Hi everyone, my name is Xuchan. Today I will present our work Diff4Steer, Steerable Diffusion Prior for Generative Music Retrieval with Semantic Guidance. This is work done at Google Research with my colleagues, Judith, Zhong, Kun, Timo, Joonseok, Dima, and Fei. It's published at the IEEE ICASSP 2025. Contemporary music retrieval and generation systems rely on domain-specific dense embeddings. With a music embedding, we can either decode them to waveforms or retrieve similar music embeddings from a database. For an embedding-based system, it is crucial to have high-quality embeddings, as the performance of downstream tasks critically depend on the embedding quality. In our case, we want to add different modalities of input to the embedding-based generation and retrieval system. Specifically, we want a user to express their preference through image or text descriptions. Then, we want to generate and retrieve music embeddings conditioned on these inputs. Before introducing our approach, we want to highlight that music retrieval based on user preference is an inherently ambiguous task. A user's preference involves a lot of uncertainty. There is no ground truth mapping between, say, a music description and the perfect music match, as different users will have different interpretations. Therefore, for such music retrieval model, it is essential to maintain diversity and be able to explore the possible intentions of the user. What are some possible approaches? We can either train a model with a joint embedding model. We can either learn a joint embedding model or JEM. The problem with this approach is that it needs a lot of pair data, and high-quality image and music pair data is scarce and is very expensive to collect. Also, a joint embedding model is a pointwise deterministic model. It does not allow exploring the user's preference, and therefore it is ill-suited for the intrinsically ambiguous music retrieval problem. Alternatively, we can learn a prior model, i.e., to use an existing embedding model and learn a mapping between from query to the existing embedding model. It is a lightweight approach. We can reuse existing embedding spaces. We can use the diffusion model as the prior model. So in contrast with the joint embedding model, a diffusion model learns a mapping between distributions. For a given image, it can find diverse music matches and is suitable for exploring users' preferences. Here we introduce the embedding spaces. For music, we use Mulan embedding, a joint music text embedding model. It is a two-tower model trained on paired music and text data. For image, we use a clip embedding model, which is a joint image and text embedding model. With these in consideration, we propose our generative approach for music retrieval. First, given an image input, we turn it into an image embedding vector, in our case, the clip embedding. Then, we train a diffusion model to generate music embeddings conditioned on these input embedding. The diffusion model is highly flexible and efficient. It reuses the existing embedding spaces and learns a many-to-many mapping. Furthermore, we can let a user to further specify their preference through semantic steering. In particular, the user specifies the steering signal through text. We turn the text into the text embedding, in the Mulan embedding space, and then apply it as a guidance signal in the diffusion model. Finally, the embeddings are then used to retrieve music from the database. We use the standard nearest neighbor search for the retrieval. We call our framework Diff4Steer. For more details about our method, please refer to our paper. We train the diffusion model on a subset of the YouTube 8 million dataset. The training set contains almost 80,000 music videos. We pre-process the videos into 10-second clips and generate the embedding pairs. These embedding pairs are then used to train the diffusion model. We did a brief search over hyperparameter configurations. We trained the model using Atom Optimizer for 2 million steps. We evaluate the performance of our Diff4Steer framework. We have 3 groups of metrics. First, in order to evaluate the quality of the generated music embeddings, we have 1, the Frechet Mulan distance, or FMD, which measures the similarity to the distribution of real music embeddings. We also measure the diversity of the music embedding generation using something called mean intra-sample cosine similarity. Second, we have a metric called M2I, or music to image, which measures how aligned the generated music embedding is to the input image. Lastly, we have several metrics for evaluating the retrieval performance, including the standard recall at K metric, and also entropy and triplet accuracy. Details about our evaluation metrics are discussed in the paper. Our evaluation results show that compared to the baseline, our framework generates higher quality music embedding, as shown in the FMD score here. And also, it generates more diverse music embeddings compared to the regression baseline. Our framework also has better retrieval performance compared to baselines. In this case, we're showing the retrieval performance through the recall at K, where K is equal to 100 or 10, and together with the triplet accuracy. The baselines here include the regression baseline and also a multimodal LLM baseline, the Gemini baselines here. Now, we present some examples showcasing our Diff4Steer framework. Here is an example of retrieved music from this image of fluorescent jellyfish in deep ocean. Let's listen to the music. And the second example is the retrieved music from this image, which is an orchestral performance. We have mentioned that our model can be used to let the user further specify their preference through steering. Here, there are 2 examples showing the steering results. In the first example, the original input says, drift into a dreamy reverie with the ethereal sounds of dream pop as the shimmering things of synthesizer blend with the hazy strumming of guitar and the hypnotic beats of the drum machine, lulling you into a state of blissful calm. Here's the initial retrieval result, a piece of calming dream pop. Let's steer it to be more energetic and upbeat. In this second example, the original input says, "Let the gentle melodies of acoustic folk wash over you as the soulful strings of the violin intertwine with the tender chords of acoustic guitar and the rich harmonies of cello, creating a sense of serenity and contentment." Let's listen to the original retrieve music. And this time, let's steer it, but in a negative way, to make it less relaxing. Thank you for watching. We hope you've enjoyed this presentation. We encourage you to stop by our poster and read our paper for more details.